gentle introduction about the AI, so that the audience, um, uh, especially if they're from medical background, they might want to understand what the AI is all about. And then I will take one example and go through the complete life cycle of AI, starting from data collection up until it gets deployed in the product. What does it mean? It's like looking at in a movie, you see that there will be a lot of things happening in the background, right? So I plan to talk about a couple of things behind the scenes and some challenges. Well, if you see this particular slide, it talks about a very simple use case of what the machine learning is all about. At the top, you see a normal software program wherein, given an input X, it is giving me some output Y. And in that function, exponential, you see that it's a simple statement of saying, hey, return e to the power of X. And then if I plot the graph on the right-hand side, you see this kind of a curve coming out. And what a machine learning would do is, you give this as the input, which is the output of this function as an input to the machine learning algorithm. And the machine learning algorithm will output that the function used is y equal to e to the power of x, right? So the main difference is that in the normal programming, you actually program the logic, whereas in a machine learning algorithm, you feed the data, and it's probably able to tell you what kind of relationship exists between the input and the output. That's the crux of the machine learning. And if I look at a traditional programming, the data and the algorithm is the input, and you get an output which is running the data on that particular algorithm. And in case of machine learning, you give the data and the output as the input, and the computer is able to tell you, going through a number of machine learning algorithms, what's the actual relationship between the data and the output. And to give you a very simple example, here is a scenario where you're trying to figure out the length of stay of a patient in the ICU. And what you could do is, using the machine learning algorithms, you give a set of inputs, the first 4 columns that you see here, and then the length of stay, the actual length of stay of the patient within the ICU. And if you give it to the machine learning, it can analyze the data and come up with some kind of equation or a relationship between the length of stay and the various parameters, or let's say features. And the ABCD here, it relates to some kind of coefficients. But the whole idea is that if that machine learning algorithm is able to come up with some kind of an equation, tomorrow in the ICU, when it gets deployed, we give the age, BP, BMI, and the SG. It can estimate what would be the length of stay. And that is an example of a simple numerical data. And if I take an image use case, this is what happens in case of let's say the deep learning, or probably might have, many of you have heard of this particular term. To decipher that, this example might help. So here is the input, which is the cats and the dogs, and you give this as an input to the in the training phase. And what the training phase does is be able to extract certain key features of the cat and the dog. And in this case, I have highlighted on the top, it could be ears, it could be eyes, etc. And then these features are fed to the machine learning algorithm. And in the actual prediction phase, if you give a picture of a dog or a cat, it's able to extract the features. And then with this set of features, it can classify whether it's a cat or a dog, right? And very similar to this would be, let's say, an image in the healthcare. It could be radiology, it could be pathology. You give the inputs, to the algorithm, and then train uh, the um, the algorithm in such a way that you tell that, hey, this is a pathology image, and this we call as, let's say, nucleus, and this is stroma, this is something else, and then these features are taken up, and you could also feed what is, let's say, the probability that this might be abnormal. And then after you train, you get a AI algorithm, and then when you feed the actual data in the normal clinical workflow, it's able to extract all of these different features, apply it through the trained classifier, and then be able to say, hey, this is abnormal, what is the probability that this is normal, etc., etc. So that's the kind of analogy that you can draw. And just one slide on what's the key difference between a normal machine learning and deep learning, because you might have heard of these terms. In the normal machine learning flow, you kind of extract the features that are required, which will be very unique for those kind of data points, and then you train the algorithm. Whereas in deep learning scenario, most of the features could be extracted by the algorithm, but of course we will see later that there are quite a few cases where there is a lot of intelligence needed to manually feed these features as well, that could help in the output. And let me start with a typical AI project life cycle. I think can you still hear me, Sushma? I see that there is a disconnect. Hello?
Can you hear me? Yeah, I can hear you.
You can still hear me? Okay, because I got a disconnect from here. Okay, so if I take a typical AI life cycle, you see that there are quite a few steps involved in this life cycle, starting from understanding the pain point and then defining what the kind of use case we are targeting. And then there is primarily four main steps in a typical AI life cycle. One is data collection, where you collect the data for the training purposes. Then you do the actual training, you do the validation, and finally the deployment. Now let's see what are the different steps that go into each of these different phases. I see some problem with the slides anyway. I think they are somehow jumbled. But let's see, take a scenario of the phase of data collection. Now, one of the primary things as part of the data collection is to do with privacy. So especially for the R&D purposes, it involves de-identifying the data, and the data can be in any format. It could be DICOM, HS7, plain pathology images, JPEG, PNG, etc., etc. And there is a need to de-identify the data before it is given for the R&D community to develop the algorithm, because typically these algorithms get developed in a lab, in R&D centers, and we have to ensure that the privacy is protected and the data is de-identified. It could be image, it could be even text. Here is a scenario where for the text to take as an input and de-identify, there is actually an algorithm, AI algorithm, to identify what are the PHI related data within the text, and then try to de-identify that, so that the data that goes for the R&D community will be already de-identified. And in this picture, you see that there are quite a few different types of approaches that are taken to identify the PHI. One is via the pattern matching, it could be via the dictionary, or a number of things happening via the machine learning itself. If we, so I'm just trying to add this de-identification, which is an activity that needs to happen during the data collection. This is yet another aspect during the data collection, which is the consent. According to the both the HIPAA as well as from the GDPR guidelines, we need to ensure that whatever data we collect for processing, it should have the consent from the patient. And of course, in your normal clinical workflow, you would always get the consent from the patient or their family members. The same thing also is applicable for the R&D development or during the development of the AI algorithms. And it should be such that at any point of time, the consent can be revoked as well. So there has to be a mechanism where put in place where when the patient gives the consent for processing the data, the purpose for which the data is taken, for how long the data will be kept, all of them needs to be present, and it should be an informed consent. And once the patient does a consent, then the data is available for de-identification and further processing. And at any point of time, as I said, there can be a revoke, in which case we have to ensure that that specific data which was consented should be stopped for further processing or deleted or quarantined, whatever. The next aspect within the data collection itself is the annotations. And in this figure, I have shown a couple of examples of what would be a typical ground truth creation, typically done by pathologists in this particular case. And on the right-hand side, you see that the annotations could be of different nature. Some of them could be retrospective, it's already annotated. Some of them is prospective, based on what you're going to do. And then the ground truth sits on the top, which has got the highest value, which is the real labeled data, which is conforming to, let's say, a biopsy report or the clinical outcomes, etc. Typically, what happens is if you take a data and then you need to label the data, the labeling is required because that's the output against which the algorithms would be trained, and that labeling is very important. And that's the reason why it is called the truth, ground truth, because against which the algorithms will be trained, and hence a lot of importance is given for the creation of the ground truth. And then the next, if you go to the next phase, which is the AI training, one of the key things is about the feature engineering. And on the right-hand side, I just put this to relate the first slide as the example that I gave. So these are all the different features. That was a simple case of numerical data. And in case of imaging and pathology as well, there are a lot of features that are present within the image that needs to be extracted, and in a way that it can be fed further to the machine learning algorithm during the training process, so that these features has something unique in there. It could be architecture of the cells, it could be the texture of the cells. There are so many aspects within each of these different features that these are the ones that could be helping us or the algorithm to identify and detect certain key aspects that we are targeting. So feature engineering is an important aspect of the training. And this is just to give the different the spectrum of processing that is required during the feature engineering. I'll just skip this. This just gives tells about the primary use and the secondary use of the data during the feature engineering. The next aspect is about the experiment tracking. Now, the experiment tracking is an aspect where typically when the R&D team or the data scientists they start working on a particular project, it is not just one time that they will use the machine learning algorithms or train the model. There will be several such experiments that they do, taking different data sets, taking fine-tuning the algorithms or what we call as parameters during the training. And there is a need to track all of these different experiments. The reason is that, especially for in the healthcare space, when we go for, let's say, a regulatory approval like an FDA, you need to justify that with this kind of data sets, with this kind of environment, I was able to get this algorithm with this so and so accuracy, right? And if we have to repeat that experiment, then you need to know all the parameters that were used, the environment configurations, what were the data, which version of data was used, etc., etc. So you can see here on the right-hand side a host of different artifacts that need to be versioned and tracked for a particular experiment, so that the main focus of this is about reproducibility of the results at any point of time. And let's go forward. Then there is the validation phase. In the validation phase, the important aspect to know is about having a very good validation cohort. So the important aspect is that typically the validation should happen from sites from where the training data was not used, right? Because you want to kind of generalize the algorithm that it can work on any data sets. So identifying the right data set and the cohort for the validation is quite important. And then there could be a lot of, let's say, false negatives, false positives that need to be discussed during the creation of the algorithm. So it's not that the algorithm gets developed by the R&D team and then it gets deployed. It doesn't happen. So there is a lot of iterative process that happens between the R&D community and the clinicians, the pathologists in this case, so that the outliers or the false negatives and false positives are also discussed and identified what the issues are. For example, in this case, on the left-hand side, you see that the algorithm is not able to identify the patches at the corners. And after the discussions with the pathologist, it was figured out that actually the ground truth was incorrect. And that is also one of the reasons that I mentioned while I was showing the ground truth, that there has to be typically ground truth is created by more than one clinician, pathologist, so that we see that if there are variations, they are minimized, and then if there is a lot of variation, there is a consensus built, so that these different aspects are moved. Then the another aspect within the validation is also about the regulatory approval. This is a picture from the FDA site, which talks about the different types of algorithms that are typically created, and what kind of justification needs to be provided for each of them, whether it's class 1, class 2, medical device, etc., are all based on these different categories of algorithms. And clinical performance assessment is also done, where the data is taken and we look at the output of the clinician or the pathologist in this case, and what is the output when the AI ML is applied, what kind of difference is there, etc., etc. This is an important aspect during the validation. Then the last one is about the deployment, where there are two main aspects of deployment. One is the feedback, and the second one is monitoring. And in the feedback, we focus about gathering the information about the performance of the AI algorithm. And typically the feedback will be given by the experts, and this feedback is taken up further for fine-tuning the algorithm, because this is also a good evidence of truth that can be considered. The other aspect is about the monitoring. The monitoring is all about when the algorithm is deployed within the product, what typically happens in the background. There is a continuous gathering of the performance of the algorithm, and we look at whether it is performing as per the thresholds that we have set. And this is a very important aspect to ensure that the safety and efficacy of the algorithm is maintained. And whenever there is a lot of a deviation, then we could raise the alert. We could also inform the management there is something happening. It also gives us insights into presence of new diseases, or there is a new variation. The data distribution itself is changing, etc., etc. This is also quite important from the deployment aspect. So and this monitoring and receiving feedback and the validation, training, etc., is not just one time. It's kind of an iterative process where the gathering data from the feedback, we use it for further labeling and further fine tune the algorithm so that we reach the accuracy that is nearer to closest to the actual ground truths. The other aspect is about the bias. I quoted here the bias spanning across the different phases within the AI development and deployment, because bias can be present in any phase. So there are biases during the data collection. In fact, even before the data collection, the designing the study protocol up until receiving the feedback. Probably I don't have to explain the problems with the bias. This is just one example where there was an algorithm that was built which heavily favored white patients over the black patients in the US hospitals. The important thing here is that the race itself wasn't a variable in this algorithm, which gives the color, but the other feature, which was the healthcare cost or the expenditure, was directly correlated with this, and because of which it could predict that it was the algorithm actually favored white patients over the black patients. And this graph here shows that people are really concerned about the bias of the algorithm. And the way that this could be addressed is also looking at three aspects. One is diversity in people, diversity in data, diversity in the validation, which means that when we collect the data for the algorithm, it's always better that we collect the data from multiple regions, so that the algorithm that is trained is kind of generalized. And not only during the training, but also in the validation, we ensure that it gets validated in multiple regions before it is deployed. I'll probably stop here. So overall, I just wanted to conclude that in the bench to bedside, which is looking at from understanding the pain point up until the algorithm gets deployed, what are the different various aspects that are there, which are unsaid or goes in the background. And there are much more. It's just a representative list and not all the different aspects within this bench to bedside case. Okay, yeah, I will stop here. These are some